Oh, yeah. You have the pointer?
Is that the pointer?
This one.
That's it.
Okay. Well, welcome everyone again, and thank you for coming. Today we have like two different departments as engineering and alloys and infrastructure of mechanics from Emilio. So please take the most of it in the pizza and do a bit of networking and chatting and mix between you all. And today it will be hosted by Emilio to introduce our presenter. So please enjoy.
Thank you, Claudia. So as Claudia said, thank you all for coming to this new edition of this engineering alloy seminars. It is my great pleasure today to introduce you to John Campbell. John is an Emeritus Professor at the University of Birmingham. And I think many of you have heard about him before. He needs no much introduction. He's a well-known scientist and engineer in the process of casting. He has made numerous contributions to the casting industry and metallurgy research, I would say, in the UK and elsewhere. His contributions have been recognized in many ways. He's an OBE. He's also a fellow of the Royal Academy of Engineering. There's even a John Campbell medal named after him by the Institute of Casting. But I think there's one thing that I would like to say is that I was particularly keen to welcome John to Imperial because I came across his book, I think it was some months ago, 6 months ago, and I really enjoyed reading it. So John has very interesting ideas and very thought-provoking ideas on the origins of metals, of fracturing metals or fatiguing metals. And the book is really very clear and very nice to read because it comes not only with new hypotheses, but also with ways of testing those hypotheses. So I thought it would be great to have John with us, and so you can all hear what these ideas are and how one can test those ideas. So a great pleasure to have you, John, and welcome to Imperial.
Emilio, thank you. It's a great pleasure for me to come to see you here and to talk. I want to talk to you about a very simple idea. It's so simple that a lot of people can't understand it. The idea is this, that when we're handling liquid metals, that, for instance, we've got a liquid metal here and we've got air above. This is the interface between the two. The interface is normally not a liquid. It's normally a solid. And it's a very thin solid. And very often it's aluminium oxide. It's got a melting point over 2000, it's very stable. And there's no problem with it being there. In fact, it's doing a good job in preventing all the rest oxidizing. However, what happens when we come to move the liquid? This now becomes very critically important. And if you have the good fortune to be in a foundry situation and you can look down on a mold and you can watch the metal coming up inside the mold, you can always see the oxide film on the surface. And as it comes up in a very special way. The oxide splits and moves to one side, but immediately reforms and splits and moves, reforms, splitting and moving, so that you see the surface oxide becomes the skin of the casting and doesn't get into the matrix of the casting. It's all the while moving to the outside. And in that way, you get a beautiful casting. Now, the trouble is that very often we don't do that. And there's a real worry if we don't, because the structure of this film is rather special. It has its two sides. Now, the underside is in perfect atomic contact with the melt and is perfectly wetted. The top side is perfectly dry and will not wet at all. And in fact, its structure, when you look under the microscope, I sometimes say it's a little bit like sandpaper, but it's much worse than that. It's very pointed, a little bit like the skyscraper of Manhattan. It's very spiky. And these two very different surfaces have key roles as the metal progresses and becomes a solid, and the effect of these two surfaces continues right through the metallurgy and influences the metallurgy at every point downstream. The worry is if at some point it does that. Now, that dry surface, spiky oxide, comes over and impinges and crunches on this dry surface with its spiky oxides, and the two never quite meet. There's always a few nanometers separating them and some entrained air, but the two never bond. They're made of these two very stable alumina surfaces. Sometimes it's chromia if it's a stainless steel, sometimes it's hafnia if it's a nickel-based superalloy. But these very stable oxides come together and never bond. I say never. They're reluctant to bonding, and it's a problem to get them to bond. And occasionally they can bond a little. But what happens now is that this unbonded interface is now like a crack, and now is floating around in the liquid like a crack in the liquid. And when we pour metals turbulently, and frankly in most foundries, the metals are poured with appalling turbulence. And the metal is falling in and scrambling and tumbling, and we're manufacturing these cracks in the liquid so as to fill the liquid with cracks. And in fact, most liquids, if you could see inside them, are a snowstorm of cracks. And all those cracks can be solidified in downstream, and we have to live with those in our metal. So all the steel of this building is full of minute cracks that, because the steel was poured astonishingly badly at some point in its history. In fact, most metals have been poured badly at multiple points in their, and, so such that we couldn't have made them worse if we'd tried. So our metallurgy has a long way to go and a lot to unlearn and relearn. So I'm keen today that we should take a new look at our metallurgy and just see how we get on. For instance, here we are. This is the good, I call it a counter-gravity filling, coming up against gravity, the beautiful way in which the surface breaks and moves to one side. This would make perfect cast material with no defects in the center. However, this is the reality where we are, whoops-a-daisy, where we're folding in the surfaces. So here's a biofilm, here are the biofilms, and there's bubbles as well. The bubbles are just as bad in a way.
They cannot see the presentation.
Ah.
Sorry. Share. Thank you.
It looks the same to me. Anyway, so this is the reality of our pouring systems. And so the turbulent surface entrainment leads to biofilms, which are kind of crack-like defects in the liquid. And here we are. Here's another instance where a folding action produces the biofilm, but also an impingement action, again, leads to a biofilm. All these things lead to double films coming together, dry side to dry side. It's fundamental to the way entrainment occurs. It's when the surface goes in, it always goes in dry side to dry side. And here are some of the things under the microscope. You can see this is multiply folded, and you see the tiny things here is about 20 nanometers or something. And here's a situation where we've polished the surface here, revealing this big tangle of biofilms. And here we've just taken off the top of the film. So we've just taken off that top so that you can see the film underneath in places. So it, it really is a double film. And this was a little experiment which was extremely valuable and helpful to us in the early days. It's done many years ago. And we took 2 small molds about the size of egg cups. And we took some liquid aluminium and we poured the 2 molds more or less at the same time, same temperature. So the 2 are identical with liquid metal. And over the one on the right, we put a bell jar and we pumped down the pressure to about 1/10 of an atmosphere. Actually, I forget, maybe it was 100th of an atmosphere. But anyway, it was a lower pressure because what we wanted to do was to expand the 2 films apart by lowering the pressure so the air trapped between them would expand, and so we could see them by X-ray, which is what these are. And sure enough, they popped up, and you can see it's absolutely crammed with cracks that we didn't know were there. Now, interestingly, this is the same metal, poured at the same time, the same temperature, same everything, except just a different pressure. Now, the reason is this, that when we form the bifilm initially, and we fold over or we impinge the 2 dry sides to make a crack, goes off into the liquid, there's always enough turbulence beneath the surface to do this. And you finish up with a very curious crack. Now, I normally pass this around the audience so they can study this in detail. It's really quite interesting. You can see that it's the most amazing crack. This is not the sort of thing that metallurgy is accustomed to, but this is something very special to liquid metals. It is a unique defect structure in the liquid metal. And it's absolutely common because when you first pour, there's always enough turbulence to scramble up the bifilms such that they all finish in this compact state. And in this way, if now I put stress, if I now solidify this liquid metal and I solidify this into the solid, now I stress the solid, this isn't going to do much because it's a very ineffective crack in its scrambled form. However, if I now reduce the pressure on the outside, then what happens now is this crack opens, fold by fold. It takes time. Each fold takes 10 or 20 seconds or something like that. And slowly, 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 it gets bigger and bigger. And finally, it's now a rather serious engineering crack, a bit uphill and down dale. Notice it's got kinks and things in it. When you look at some of these, this crack here, it's got a right angle and here's other kinks. This is exactly like the cracks we see. They never really straighten out, but they are serious as defects now. And so if we take, for instance, a machine, a tensile test piece out of here, it will almost fall into 2 pieces by itself. its properties will be fantastically low. So we need to keep in mind the fact that the bifilm can be in these two states, a convoluted state, or what I call this sometimes a furled state. You know, with a sailing boat, you furl the sails or you unfurl them. And this is, when it's open, I call it unfurled. And the unfurling process, excuse me, need some water. The unfurling process can happen in an amazing number of different ways. And we'll talk about some of them as we go through this afternoon. So when I show this picture to people in the aluminium industry, for instance, and they say, oh yes, we get cracks just like this. This is actually a super duplex stainless steel. And I just show that because this is a problem right across the metals industry. It's not just aluminum, and it's not just steels. It's the super alloys. Nearly every metal alloy system you can think of has this same problem. And we can have a quick look at the simple physics of why it occurs and the critical conditions under which it occurs. Because if we just look at the surface, and the surface is being tensioned by surface tension to keep it flat, but it's being perturbed by turbulence here in the liquid. So this is perturbing the surface with a certain velocity. And we can write down the critical condition at which these two forces, the inertial pressure in the liquid and the surface tension pressure, become equal. And we get a critical velocity of 0.5 meters a second. And I said to one of my students, I produced this on the back of an envelope and said to my student, do you believe this? He said, oh, no. I said, neither do I. So, but anyway, I asked him to go off and test it. And he took a small casting about the size of my phone, and he came down, brought the metal in, went under and came up into the mold underneath at different speeds. And then we then subjected this to some dye penetrant to count the length of cracks. And then we took the whole casting and did a 3-point bend on it, see how strong it was. So these are his results. And so these are the crack lengths, and what you can see, this is the velocity here. So up to 0.5 meters a second, there's no cracks that we could find. And suddenly at 0.5, cracks appear, and then nothing, something, nothing, something terrible, nothing more or less. So here is chaos. And it's interesting to see chaos on plots of graphs. Here you would expect chaos, because this is now being controlled by turbulence. And the turbulence is something that's rather chaotic, and sometimes the metal will jump one way and sometimes it jumps the other, or may not give you a crack. So this is an expected behavior. But down here, the castings you make are safe, free from cracks. Okay? And then when we looked at the strength, had good strengths up here, and then a cliff edge here, and then awful strengths along here. And it was this result here, these two castings, that really alarmed me. Because These two castings had virtually no cracks. They looked perfect on X-ray, and they could have gone out from the foundry, and the aeroplane could have been hanging from the sky on these two castings, but the strength was there. They had nearly no strength, but they'd passed all the quality tests. And that result so shook me, I changed all the research at Birmingham on that day for the next 15 years. And we researched the problem of how to get rid of turbulence in castings because of the danger for normal castings. We were living with dangers we didn't even know about. These are two of the castings. This one has got, well, when you bend something, you expect a crack to go along the axis of the bend. Well, there's not one crack on the axis. There are these cracks just slightly off the axis, one going down here, another one going across here, another one down the back you can't see. And that gives you the clue as to how they formed. It's the randomness that tells you this is due to the randomness in the way the liquid jumped and splashed inside the mold to create these cracks in the liquid state, which then get solidified in. And this one was done less than the 0.5 meters a second, so that was safe, no cracks. So if we look at the properties and the microstructures, this is one of the ways in which when we first pour, the bifilms are scrambled into the liquid in a compact way, but then the grains start to grow. Now, the dendrites can't grow through the bifilm because of the air layer. So they reach the first film. There's the layer of air before it gets to the next film. Oh, clearly, the dendrites can't grow through the air. So all they can do at that point is push. I say push. This is a colloquialism used amongst researchers. What it means is this is trembling with a Brownian motion against the tip of the dendrite. So every time it moves away, more liquid can come in, and so it looks like the interface is being pushed. In fact, as it moves away, liquid can access and freeze, and so it's a one-way process. So it's very convincing as a pushing action. But anyway, so as our dendrites start to grow and they push, they slowly push, and they slowly flatten out the bifilm. So we get our engineering crack back again, and properties now really fall a long way as a result. And this is the kind of thing we see here. So some of the cracks have been flattened, and this, for instance, is how we see facets. Very often in the fracture surface of a casting, you get a kind of facet, and this is very common. So this is a kind of facet formation, and here we've got a kind of sine wave here, which again you see on some fracture surfaces. And here you've got a complete mess of films that are still being pushed ahead in a heap. And here's a typical I think it's a 6 millimeter diameter test bar, which has been fractured. And this is the fracture surface. And what you can see is that here the dendrites have grown and have pushed the film ahead here, and the dendrites also grown and have pushed it here. And so this little mountain range down the middle is all the spare oxide film that's been pushed ahead of the two lots of dendrites as they've grown towards the center and just piled up the film in the middle. And so these are really quite large crystals, whereas this is from the same casting. It's just that at this part of the casting, there was a big back wave and a big splash, and a big bifilms were formed. At the other end of the casting, that happened to fill nicely. And so this part of the casting has all the small population of bifilms that were in the original metal that was before it was even poured. And this is the trouble in the metals industry. Now we're recycling a lot of our metals. The metals get poured by all sorts of people, made into all sorts of products. It comes back to the foundry, gets melted down, and we get all its inherited bifilms free of charge. And so these things come round a second time. Very often they're scrambled, but they're something we inherit in the system. And so in the foundries I try to set up now for the future, we pay a lot of attention to dealing with the inherited bifilms, and having dealt with them, to clean them up, you've then got to make sure all the rest of your processing doesn't reintroduce bifilms before you make your cast product. Anyway, let's move on. That casting on the left, what we're looking at there is that our big bifilms. In fact, there's no metal to be seen on that fracture surface. I mean, the whole surface is covered with bifilms. Now, this is different. This has got some bifilms, but some metal is to be seen. And here we are. What you don't know is you're looking at a bifilm there. And so you remember how that formed with the two lots of dendrites growing either side. Now, the fracture goes through the center. And so now we have, I need more hands to do this. We have two fracture surfaces with dendrites just underneath the surface. And we are seeing those dendrites through the oxide film, which is so thin, you don't know it's there. Which is why we never see, we think we've never seen bifilms. Nearly every one of you would have seen bifilms without knowing it. And this is an occasion. There's a little part there, you just see it, where the bifilm is actually folded over twice. And that tells you you're looking at a film. Whereas here, this ductile dimple structure, at the bottom of every dimple, there's a silicon particle which wouldn't have fractured except that it grew on a bifilm. You remember the bifilm had, the center was unbonded and dry, but the outside was in perfect atomic contact. And what happens is that particles, like silicon particles in the aluminium alloy, nucleate and grow on the bifilm, on the wetted surfaces. So they can grow on both sides of these things. And so when your silicon particle breaks, it's broken because it had a bifilm growing up the middle of it. And it's got nothing to do with stress. It's broken because, as I say, it was always broken. That's the way it grew, with a crack up the center, which was a bifilm crack. So most of our cracks have nothing to do with stress. They just come apart at the bifilm. Anyway, so I was saying at the bottom of each one of these ductile dimples, there's a fractured silicon particle. And let's look at the next slide. Yes, here we are. Here's our fractured silicon particles. And here is the ductile matrix. And what you can see is the matrix is perfectly ductile because it's necked down to 0 thickness. These knife edge arêtes are pretty well truly knife edge, which means that if we'd got a truly ductile material which we put into our tensile test machine and just pulled, it would neck down until finally come away at a point, like a piece of plasticine. And that would be its failure mechanism, a perfect plastic failure. And here we've got perfect plastic failures with all these knife edges around here, whereas here you've got perfect brittle failure, but it's not brittle because the silicon is brittle. The poor old silicon only fractures brittly because it has bifilms all the way through its center. And here's another instance of the bifilms and the way the structure of inclusions relates to the bifilm. And in every case, in fact, every time I've ever looked into any inclusion or second phase, it always nucleates and grows on a bifilm. Now, someone at some stage you're going to find an inclusion or a second phase that doesn't nucleate on bifilms, but I haven't found one yet. But maybe they do exist somewhere. But here, they certainly grow because they nucleate and they grow on bifilms. And here is a situation. In this instance, the beta ion grows as a monoclinic platelet. And again, we start off with our bifilm originally like this, but the beta ion nucleates on it and then grows, and because it's a monoclinic structure which grows as a plate, it straightens out and you get these beautifully straight crystals with a crack up the center. I could say more about the cracks, but we don't have a lot of time today. But the reason that the iron impurity in aluminium alloys is so damaging is because the iron particle grows as a monoclinic structure and straightens bifilms to make the bifilms into engineering cracks. And the longer the cracks grow, the more the properties come down. And that contrasts with this situation, where now we've got alpha ion particles. The alpha ion is a very nice cubic lattice. And because it's a cubic lattice, it can grow in any direction it wants. It's not constrained to grow as a long platelet. It can grow in a compact crystal if it wishes. And so back to our convoluted bifilm is when it starts in the liquid. And now the alpha particle nucleates on it. And now the alpha particle can actually grow around this corner and grow around that corner and that corner and that one. And so wraps around this particle and freezes it in place so it can't open. And now you have a completely different situation. You have a much better property because you freeze in your bifilms in a convoluted manner. And you can see how they're all wrapped up inside here. Even so, some of the bifilms escaped into other particles, but basically most of it is raveled up and unable to escape. unfortunately, as I say, not all of it gets ravelled up, and some of it still remains to bring the properties down. So the biofilms are still a damn nuisance, frankly, because they do affect properties, even though you do your best to wrap them up with the metallurgy. And here's another instance where the beta iron has grown long crystals, and here's one. But here, the beta iron has only grown on 1/2 of the biofilm and straightened the half out. But on the other side, so there's the beta particle on one side, but the other side, nothing happened to grow. Nothing arrived there to nucleate. And so that was free as an oxide film to wander off and would do whatever it wanted. And of course, as, for instance, the hydrogen increases in these regions, the hydrogen will blow it off, or if there's shrinkage here, it'll actually suck it away. So suck it away like this, but there are dendrites here. And so this second film will start wrapping itself around dendrites. And that's what's happening here. It's being pulled away here and pulled into the dendrite mesh. So the biofilm is clearly a very good initiation point for porosity in castings. But frankly, the porosity is a secondary effect. The biofilm is the primary problem and the primary defect. Porosity is a secondary issue which the biofilm can give you, again, free of charge. Costs nothing, can make the casting as bad as you like. And these are some of the fracture surfaces. This is in a magnesium alloy. I mean, they're just amazing structures, which, as I say, very often on a fracture surface, you're not seeing any metal. It's always you're seeing half of the biofilm. And here again, this is the same magnesium alloy. And now the biofilm's in a much more crunched up situation. But although this is obviously a film, all of this as well is again biofilm. It's just that it's been crunched up incredibly small. But as I say, everything you're looking at is one of the biofilm films which has come off on that side of the fracture, and the other film from the biofilm will be on the other half of the fracture. And here is a very bad piece of metal turning in which we cast this nickel-based alloy. This is a beautifully ductile nickel-based material, but we cast it really quite badly in the early days before we knew how to cast the stuff. And what you can see is it's full of bifilms because the person turning had turned with a rather blunt cutting tool, and the cutting tool has torn open the bifilms on the surface. It's sort of ripped them open to make a really bad surface. And you can see they're everywhere. This is another shot from, again, I think it's the same nickel-based alloy. So, okay, so that's a little bit of background of the metallurgy. Let's look at the casting technology to see what might be done about it. Now, I don't know whether any of you have been into a steel foundry, steel works, seen steel poured. Well, if you haven't been, if ever you get the chance, you must go, okay? It's one of the most frightening experiences you could have. When you see the furnace being tilted and pouring out the steel, this great heavy liquid is thundering down, much more impressive than Niagara Falls. And it's so heavy and it's coming over, and it's just the most daunting thing you ever could possibly see. But of course, it's manufacturing biofilms like there's no tomorrow. Okay? So the steel in the furnace, this is a little arc furnace here. It's about a 5-ton arc furnace by the look of it. The steel in the furnace would have been really quite good because it sits in there for some time while it's treated and get the composition right and the carbon out and whatever. So it's been in there for about an hour or so, during which time, in this very shallow bath, there's plenty of time for nearly all the biofilms to float out. So your steel's in really quite good condition in the furnace. And then, horror of horrors, you tilt the whole furnace, it all thunders out into a ladle at least 3 meters down in a pit and completely destroys all that good quality. And, okay, the oxide biofilms are very different in density in steels. So they rise very quickly. The big biofilms will float out really quite reasonably quickly. So by the time the ladle's brought up out of the pit, carried over the foundry, comes down into the place where the castings are going to be made, and they open the stopper on the bottom. During that time, a lot of the defects will have floated to the top, and on top of the steel, there's a layer of slag now about 100 millimeters deep, which is all the biofilms which have floated out. And when you think they're only nanometers thick, which is what, 10 to the minus 9, is it? And we've got now something measured in centimeters on the top, 10 to the minus 2. That's 10 to the 7 depth of biofilms that we've got. It's 10 million biofilms deep in the top of the liquid steel. And I would think that's probably rather an average sort of number. Even though you've got out all that number, there are still millions or billions left, unfortunately. So the steel never really gets over that first pour. A lot comes out, but a lot stays in. And this is why our steels will never be much good while we have this technology of melting in a furnace and pouring through a height of 3 meters or so into a ladle. And there's got to be some serious rethinking about how to redesign steel making equipment. It's not just steel. See, this is the aluminium industry. And it's not this chap's fault that this is what he's overseeing is a biofilm manufacturing process. I mean, we're completely destroying the quality of this metal by pouring it through this height of a couple of meters. And the fault is that our metallurgical industries are fundamentally wrongly designed. Now, chaps, if you want a job for the future, there is an opportunity. Honestly, there's huge amounts of work got to be done in the metals industries to sort them out and do better than this. And I mean, one of my big jobs still, I'm working with operations to set up better casting methods where we don't pour, where the metal only moves by the counter-gravity method. Remember the special magical method where the metal, the surface oxide never enters the matrix. So let's just talk about some gravity filling systems that we have at the moment, just to give you a feel for where the industry currently is. So this is where we are, making all this mess. And it's very important to know that in vacuum melting, every vacuum melting and casting unit pours with gravity. So every vacuum melting furnace makes bifilms and destroys the quality of the metal. And you may say, oh, how is that possible? It's in a vacuum. Melting and casting vacuums are different to other people's vacuums. You may have microscopes with wonderful vacuums, but they don't occur in the metals industries where you're melting metals, and they cannot occur. The metals industry is doing its best, but when you've got molten metal sitting in a refractory container, the refractories are outgassing so fast that the vacuum pumps can't keep up. And so your atmosphere is like dilute air. That's all it is. It's a terrible vacuum. And so every time you pour, like this furnace, this is just a laboratory furnace, like you'll have them here in Imperial College, where they're going to pour through some height. This height H is the critical damaging feature. All your castings will be full of bifilms. In fact, exactly similar bifilms as if you had poured in air, because the geometry hasn't changed. So your bifilm geometry won't change. All that will happen is the bifilms in the vacuum will be thinner. So they're even more difficult to see than they were when you poured it in air, but they're still there, and they're still about as bad as they were because the areas are there, the geometry hasn't changed. And in fact, I come across more and more failures from vacuum castings with people just pouring these horrible gravity pouring systems. Say the vacuum is a snare and delusion. I could make a better casting by pouring in air and pouring carefully via a good running system. Much better casting than that machine can do. So we're missing out the top of our slide, but anyway, never mind. The top there, if we pour in the top, when we want to make, if I want to make a casting, I can pour the metal into the mold in the top, which is going to be bad because it falls freely and splashes and tumbles. If I come in at the side, that's also bad. If I come in at the parting line, because this will be made in a two-parted mold, so it's very common in the industry to come in at the parting line. But then again, in here, it's going to fall a bit. I haven't talked about the height of fall. You remember the half meter a second, the theoretical critical speed. And what I say to my own students is, how far, therefore, does the metal have to fall, accelerating, getting faster and faster under gravity as gravity accelerates the metal? How far does it have to fall before it reaches half a meter a second? How far does it have to fall? Have a guess. Meter? Any advance on a meter?
Less than a meter, 0.1 meter.
Well, it's easy to work out. It actually works out at about 1 centimeter. Okay? Which is so ridiculously small distance that what it means is any fall is going to be more than 1 centimeter. So what it's telling you is you must never let the metal fall. You know, otherwise you're in danger of exceeding the half meter a second, which means you're in danger of enfolding the surface. So again, here we would just about be in danger because the metal would, if we came in at the parting line, it's going to fall about 1 centimeter. So coming in at the parting line is no good. So we can come in at the bottom horizontally, still not very good because now the metal has gained whatever velocity it has, which is probably at least 1 meter a second or 2 meters a second, comes in at the joint and then goes straight across the bottom, hits the far side, at faster than half a meter a second, jumps and splashes back, again, it's useless, okay? So all these methods are no good, which are used within the industry for getting the metal in here. The one that does work, if you're careful, is the one that comes up, having come past and under and up. That you can get to work if you're careful. But the one that works beautifully is the final one there, where we never pour at all, where we only bring the metal uphill. And you might say, hang on, how's it possible to only come uphill? You design your foundry differently. So you start with your metal low down, and you put in it a pump. And you use a pump to bring the metal up. We never use gravity. We always use counter-gravity to move the metal. And we don't move it too fast, we don't move it too slow. We bring it up at the correct speed, just under the half meter a second possible. And that's the way we make castings. I try to make castings nowadays. And that's the way I design foundries. And they are miraculously different from foundries where the metal's poured. So, counter-gravity systems. Here we are with our magical, wonderful filling mechanism, which is a natural process. And thank God there's a natural process we can fall back to, which works beautifully. We do have to get the velocity right. For instance, if we keep the velocity at 0, the metal is very safe. Nothing happens to it, but it's not very good for making castings or any products really. So if we come in too fast, obviously the metal jumps up in the air, falls back and churns away, and we're in trouble again. And the critical half meter a second is just that velocity at which the rate of rise of the surface is always held in place and in check by the surface tension of the metal. And that works beautifully. This is the condition I use. The half meter a second is theoretically correct. This is where John Campbell pushes the system to, and can get away with it, but it's a risk. By the time you get up to 1.1 or 1.2 meters a second, you know you're going to have problems. Okay. So here's a machine, which is a counter-gravity machine. So you've got the metal here. You can put in an air pressure into the furnace and force the metal uphill, counter-gravity, into a die. Then you wait while it solidifies. When it's solid, you open the die, take out the casting, close the die, and then next metal goes in. What could be simpler? Anyway, it's completely no good. I wouldn't have one of these machines if anyone wanted to give me one. The reason is, in reality, this is the reality. The metal arrives on the forklift truck and it tilts, pours into the filling chute here with terrible turbulence. There's a lot of damage. And then it comes and pours again falls again here, does even more damage to the metal. And all this damaged metal is then pressurized up the riser tube to make a casting as bad as possible. Now, if that weren't bad enough, after this is solidified, the die's open, the metal's taken out, the die's closed again, the gas pressure is reduced to 0. And the metal then immediately falls back down here and goes whoosh at the bottom. And all those bifilms which have settled out harmlessly on the bottom are now whooshed and stirred up again to make sure that they all go back into the next casting to make it as bad as possible. I mean, it couldn't be worse if you designed it to be as bad as possible. Okay? This is a horrible machine. I won't have anything to do with it. So this is what I built. And this was made the Cosworth racing engines, and frankly was a godsend to Cosworth. It really got them out of a trouble. They finally got engines which finished over the line instead of breaking down halfway round, or worse than that, 50% of the engines failed by fatigue on the test bed. They never got out onto a racing car. So when you're losing 50% of your engines for fatigue, this is a recipe for going broke very quickly. And anyway, when this machine came along, it never once pours metal. See, the metal only ever goes uphill with the pump into the mold. Say that from the day this machine came into being, actually Mark I machine to be truthful, but this is similar. The day that the Mark I machine came into being, no engine ever failed again. So we came from 50% failures on the test bed to 0 overnight. So, you know, the whole business of fatigue and being able to control fatigue, I see as being primarily a casting problem. It's the way we treat the liquid metal which controls whether it is or isn't going to fail by fatigue. And this actually is still the fastest production process used throughout the world. And it's still used by Ford of America and General Motors. And it can make the V6s and V12 and V9s, 6s, 8s, whatever they are. The old internal combustion blocks, which are now soon to disappear, but for a time, and still today, this is the fastest machine in the world, beating high-pressure die casting, for instance, and makes far better blocks as well. I mean, the blocks don't fail. So this 50% fatigue failures and 0 failures afterwards, this was my first big success to prove that something like bifilms were really happening. And what's happening nowadays, just for your interest, is that this is an outline of a system which I'm helping build in Yorkshire. The machine is now built, it's just fired up, it's drying out its refractories, and we hope in the next month to be producing our first cast metal. And we want it to be the best metal aluminium alloys in the world. We want to beat everybody if we can. And so that's what we're wanting to do. And how it's happening is we've got a stack furnace here. Where it melts down. The oxides on the surface are left here, whereas the oxides in suspension inside the material are still there in suspension in the metal. And we allow them to sediment out. And the material, then the good quality material, we put through a pump and pump up into molds. Now, I see we've got an interesting situation where I'm going to run out of time massively. You know, some lecturers have no idea, you know. You think they would know better. And And I'm just wondering what we should do about that. Should I come back next month and with the other half at next month or something?
Well, welcome to,
I mean, it's just a question of what we do about it.
We'll be delighted to have you here next month.
Yeah. Because, what slide am I at? Yes, I mean, really, there's quite a lot to be said, and what I really wanted to go on to talk about was the secondary, the remelting market for aluminium, sorry, for metals, mainly for superalloys, and the vacuum arc process, which makes most of our discs, for instance, for gas turbine engines, for aircraft. And at the moment, these discs are exploding in flight, all because of bifilms, which the industry hasn't taken on board just yet. And so there are still hugely important areas that we haven't had time to cover today, but maybe on a future occasion we could take it up, and I particularly want to go through the various aspects of the failure modes, like, for instance, stress, corrosion, cracking, and hydrogen embrittlement, which is one of your favorites, Amelia. And I think we've got a lot of talking to do there, a contribution from both sides, which could be very helpful. So please accept my apologies for not having delivered what I wanted to deliver, but I do remain at your service for visiting you again, unless you say, we're not having that chap Campbell back. But anyway, it's been a great pleasure to meet you, and I'm sorry I've taken all our time. Those of you who may wish to stay and ask questions, I'm very happy to answer questions. Thank you.
Inspiring presentation, and for sure we'll be happy to have you here. So it is about time, so I guess some of you may have to leave, but if not, please enjoy pizzas, and if there's any pressing questions, otherwise just please, John will be here, we have no rush, so please grab us outside to pizza and come here to discuss with us anything that you may want to talk. Thank you. Thank you all for coming.
Well, actually, it was very interesting. Thank
Other
you.
questions online?
Yeah,
Okay, yes. Yeah.
So we have like this one. With such a slow filling speed, are there any trade-off in terms of the features that can be attained in the casting? For example, premature solidification along thin features.
Yes, I mean, these are good questions.
Yes, I can forward it to you, and then maybe you can send me the answer. But it was very, very interesting. I'm looking forward for the second part. With all the solidification findings. Would you like me to answer? It was like for Thomas.
Can you email those to me?
Yes,
Thank you.
I'm just going to stop recording.
Hello.
Excuse me.
If you have sometimes just one question, you don't mind. Before coming here, I was actually working for a steel mill company, and my question before coming here, I was working for a steel mill company.
Oh yeah.
And what happened? I was in research. Metallurgy department is we have hydrogen embrittlement testing, and